we use hydro, that's the root, or you can call it hydraulic field. And it's actually for the groundwater movement. So groundwater is one word. And in many cases, we also call groundwater pore water. It's the same thing. But these are two words. So first, let me offer an overview, because some of you are not come from an area, related to porous materials. So when we are talking about the groundwater movement, so the background is actually the water, the movement of water. Usually the background is movement of water through the surface of our planet. So for that one, we call the water actually have a cycle. So for example, you can start from any element of the cycle. For example, the water, we can start from ocean, that we have bulk water. And the bulk water, they can evaporate. It turns into a vapor, right? And the vapor form clouds. And then clouds, we have condensation, then we can have precipitation. And it means we have snow, we have rain. And eventually they come to the ground, become bulk water again. And the bulk water, they have two routes to go. First, they can just run on the surface, so that is surface water. For surface water, we have streams, we have rivers, we have lakes, ponds, and eventually they go to the ocean. And another route is, they can get into the ground. So that process is usually called infiltration. And if we are talking about, the process of soil moving through a soil layer, we call that percolation. And once water get into the soil, usually what happens is that, we have something called a water table. So above the water table, the soil is not saturated. So that means, we know that we have pores between soil particles. It's not saturated. That means not, only part of the pore volume is occupied. And when it's saturated, that means all the pore volume is occupied by water. So sometimes the unsaturated zone, it is called a vadose zone. And the saturated zone is called a phreatic zone. It's the same thing. These words can be used interchangeably. So, and the surface water and the groundwater, they can interact with each other. For example, surface water can become groundwater and groundwater can become surface water. For example, we have something called artesian wells or artesian ponds. That means you dig a hole into the ground, you find the water coming out automatically. So that is an artesian well. So in those things, they can cause the interaction between groundwater and surface water. And also groundwater can also get into the ocean. So you can see that this is a cycle. And also sometimes the water need to go through not just soils, air, they can also go through plants. So for example, the roots of the plants, they can take water. And also the water can get can move through the body of the plants and eventually get to the air, and that process is called transpiration. So it's similar to evaporation, but you need to go through the body of the plants. So this is the cycle of water. Sometimes we call it hydraulic cycle or water cycle. So let me for the hydraulic cycle. So it's hydrologic cycle. As I mentioned, there are two routes. And one is surface water, and the other one is groundwater. So surface water there are two words, and groundwater is one word. And for groundwater, we have saturated, we have unsaturated, zone, or sometimes called they, those, zone. And we have saturated zone, and some people call it phreatic zone. And the water flow in the unsaturated zone, that's unsaturated flow. So some people in soil science, they prefer to call it variably saturated zone. It's saturated flow. And for the saturated zone, we have saturated flow. And this is the overview. And again, this hydrologic cycle is called a water cycle. So it's the movement of water through the surface of the earth. And next, so let's take a look at one key physical law in describing groundwater movement. So that is Darcy's law. So Darcy's law looks like this. So it's JH equals minus K times the gradient of H. Does this equation ring a bell? Does it look similar to something that we learned before? You had a very similar equation for heat transfer, right? Actually, I forgot to mention the name of it. It's called Fourier's law. So for that one, it looks like JT. So that the heat flux, T is for thermal field, H here is for hydraulic field. JT equals minus lambda, that's the thermal conductivity, right? Times the gradient of T. So that is Fourier's law. And this is Darcy's law. And you may see some other laws, for example, for the movement of solutes, particles, we have something called a fixed law. Fixed first law. And for the movement of currents, we have Ohm's law. So they have the same form, but they just have different symbols, with different physical meanings. It's all say that the flux of a conserved quantity is proportional to the gradient of that quantity. So that's kind of a general thing. But here there's a negative sign here. Don't forget about this. And also it's proportional to the gradient. So that means there's a proportionality constant between them. And that proportionality constant usually has a clear physical meaning. And in heat transfer is thermal conductivity. So the higher the thermal conductivity, the fast that material can conduct heat. Here is the same thing. This is called a hydraulic conductivity. So the higher the hydraulic conductivity, the faster this porous material can transfer water. So this is called heat flux or thermal flux. And this K is called hydraulic conductivity. Oh, sorry. It's water flux. Apologize. And the H is water head. And before I move on, so I want to ask you guys one question. So here's my question. So there's one statement, that is, water moves from a location with a higher something to a location with a lower something, the same thing. And I have three options. The first one, I have four options. So the first one, A, elevation or location. B, pressure. C, energy. D, velocity. Which one do you think is correct? The correct answer is energy. The reason is that energy has different forms. We have, for example, for water, if we're talking about water, it has potential energy. So potential energy is a relative term, so it's related to its position or elevation. And we have kinetic energy. And we also have potential. So potential energy is just the elevation. It's the elevation. So in water, usually with the rho g h is this h. And the kinetic energy, usually we represent it using, we know that if we are talking about an object, the kinetic energy is 0.5 times m, the mass, times v squared, right? But if we are talking, we are not talking about macroscopic object, we are talking about 1 point. So we should talk about the quantity per unit volume, right? So in that case, we don't use mass anymore. We use mass per unit volume. So that's rho, that's unit weight, right? So kinetic energy is 1/2 times rho times v squared. And this one can also be converted to a length or a height. So the way to do that is do it in this way. So the equivalent height is v squared over 2g. And then for internal energy, we can split it into two major components. So one is pressure. And the other one is thermal. So their internal energy, that means this energy is stored at the particles, the molecules, the atoms. And for the molecules and the atoms, the pressure is determined by how far they're from each other. If they're too close to each other, they're gonna be like a repulsive force between them, right? They try to push each other away. If they're too far from each other, they're gonna pull the other one towards itself. So that's the reason for pressure. For example, if we have a cylinder of gas, we try to push the gas, we will get a pressure because we try to push molecules closer to each other. So we will increase the repulsive force between them. And the thermal energy is caused by the collision between particles. Because the particles, they're very small, so they're not stationary. So they're we know that they have random movement, right? It's called Brown movement. Because they move around, so it's very likely that some of them will have a collision with another particle at some time. And the intensity of that collision determines the thermal energy. So for example, if we have a gas, we raise the temperature of a gas, what's going to happen is that we're going to make the particles, the molecules, move more dramatically, and they will have more dramatic collisions with other particles. So that's temperature is just like an average indication of that. We explained that before. So for thermal, we use it for temperature, so it's a different story. But for pressure, we know that is P it can be equal to rho G H. So this H we call it HP. So you can see that for all of them, this first one we call it Hz. So you can see that all types of energy, they can be measured by H. So that's the height. Actually, to be more specific, that's the height of water column. For example, if we are talking about pressure, when we say pressure head is something, that means at one point, this HP is the height of water above that point, and need to be above water. And if it's kinetic energy, how to measure it? For example, if we have water move through a pipe, in order to measure the kinetic energy, we just need to stick another pipe to the location of interest. And if the water moves really fast, we will see that the water level will raise up. And that's height of that H is this HV. And elevation is just you just need to take a look at the location of the point. You compare the elevation at that point and something called a reference point. That's a proper technical term is called a datum. So we said datum is here, then the elevation head is just from here to here. The vertical distance from that datum to the point of interest. So this is the meaning of three things. And we add them together, we will get, so H is the summation of Hz plus HP plus HV. And one thing to keep in mind is that this term, HV, so the velocity head is usually negligible in porous materials. Because we have very small pores, and it's very hard for water to move through the pores. That will consume energy. So because of that, the velocity in porous materials like soils usually cannot be that high. It's very low, so the corresponding velocity head is much smaller than the elevation head and pressure head. So usually, we don't consider this one in porous materials like soils. And for H, for Hz, it can be positive or negative depending on the location of the point relative to the datum. So can be positive or negative. On the location let's see the elevation more accurate. The point relative to the datum. Datum is the reference. Is a zero. Is the point? Is the level with zero the elevation head. And HP can be positive and negative. So positive, that means we have pressure. And this is usually what we have in saturated soils. And if it is negative, then we have, it's not tension anymore, we call it suction in porous materials. And this one, we have suction in unsaturated soils. That's why when you have totally dry sand particles, the particles will not stay together. But if you add a very small amount of water to it, that water will hold soil particles together. The reason is because of that suction thing. So then, with this understanding, let's take a look at the Darcy's law again. So you can see that we spent this time to explain what is head, what is H. So this H goes back to Darcy's law. So energy here, this is corresponding to H. So H is the total head, the total energy. And this goes to here. Actually, this equation tells us two things. So the Darcy's law tells us two things. So first, water moves from a location with a higher energy or water head to a location with a lower energy or lower total water head. Right? That's the first thing. Second, the flux, water flux, is proportional to the gradient of the total water head. That's the second thing. And also, there's another thing that is, which is not obvious, which can be not obviously seen from this equation, but you need to know is that when water moves from one point to another point, we need to consume energy. That's easy to understand because in porous materials, as I mentioned, we have pores, and we have those viscous force between water and the solid particles. So when water moves through it, we need to give it some pressure or give it some energy so that it can move through that. And because of that, we will have a drop in the total water head. So for example, we have a tube filled with soil particles, and if we connect it to two water tanks, one with a higher water level, one with a lower water level, what's going to happen is that water is going to move from the side with the higher water level to the side with lower water level. And the water velocity is going to be proportional to the difference between the two water levels. So that's where this equation came from. So it's based on that experiment. So people change the water levels on two sides, so we will get different difference in H. And people find that they will get a different flow velocity. So that's where then they found that the flow velocity in 1D case, the water flux in 1D case is just the velocity. In 3D case, it's called a flux. So in 1D, the flux or the water velocity is proportional to the difference in water head, and also the traveling distance from the start point to the end point. And here we call it delta H, but if we write it in a 1D format, in 1D, it's look like this. V, this is the scalar. V equals minus K times the change in H over the change in L. So this is the gradient. So L is the traveling distance, and delta H, dl is traveling distance, and dh is the head loss or head drop. And this one, dl, the whole thing, is the traveling distance. So this is the 1D version of it. And I want you guys to differentiate it, a few confusing terms. So first, sometimes you heard one word called flow rate. Flow rate is not velocity. So flow rate, Q, is velocity times, in 1D case, A. A is a sectional area. So flow rate has a unit of cubic meter per second, and velocity have the unit of meter per second, and this one area have a unit of square meter. So you can see that flow rate says the volume of water that we will collect over a unit time. So it's not different from velocity. Velocity is how fast the water moves from one point to another point over a unit time. So this is the first confusing thing. Second, so the V or the flux, in 1D case, you will get a V here. This V is called Darcy's velocity. And it is not the real velocity. The reason is that for Darcy's velocity, we assume that the water moves through the whole cross-section of soil. However, in reality, we don't have the whole cross-section open. We only have part of it. We only have the part which is not occupied by particles, right? So the real case, this is Darcy's velocity, and the true case is that we have something like this. So we only have so the hatched area is the real pathway of water. And so based on this understanding, so which one do you think would be higher, the Darcy's velocity or the true velocity? True. Yeah, right. Like for example, if I say that, hey, 5 of you need to move through this pathway within the same amount of time. So if the pathway is really big, you can move very slowly, right? But if I narrow the pathway significantly, you guys need to move faster so that you can get it done with the same amount of time. So that means V is smaller than V true. So keep this in mind. Many people introduce Darcy's law without mentioning this. So they don't know what the V or what the flux they get. It's not the real velocity. So darkness velocity can be calculated using the flow rate. But the true velocity, you can measure it using a real water velocity sensor. So if you use a sensor, you measure a water velocity, you compare it with the darkness velocity that you calculated using a test. You find that, oh, wow, the one that I measured using a sensor is much higher than the darkness velocity that I calculated using Darcy's law. So this is the second thing. And the third, if you look for the literature for water movement, you may see another form of Darcy's velocity. So the one that we know here is JH equals minus K delta H. But some people write it in another way. Some people write it as JH equals minus kappa. It's like a small letter k times this k, I think it's kappa. Oh, right. It's bad. What's going on with this pen? Kappa mu, then the gradient of P. And the P here is pressure, or equivalent pressure. So if people do it in this way, this K is called permeability. It's not a hydraulic conductivity anymore. So in some of the presentations that I attended before, some of very experienced geotechnical engineers or researchers, they use these two things, hydraulic conductivity and permeability, interchangeably. It's not correct. So they're different things. So hydraulic conductivity, you can see that's the property of the soil, the whole soil, including both soil particles and water. But permeability is only a property of a solid skeleton. And to consider the water property, we use the viscosity. So you can see that we split one thing into two. And this is a property of solid only. And this is for the whole soil. And this is viscosity. So we know viscosity, that's for fluid. In this case, it's for water. And based on these two equations, actually we can obtain the relationship between permeability and hydraulic conductivity. That is, let's do it in this way. So this one equals minus kappa mu, and we know P equals rho GH, right? So rho G, they're constants. So we're going to assume that the water density is a constant. The water density is a constant. So, and also the G, the gravity constant, is a constant. So this P is rho GH. So we can take them out of this gradient operator, right? So we can have rho G times H. And if you do it this way, you will find that, now we get a relationship between K, hydraulic conductivity, and permeability, small letter of the kappa. So it's rho G kappa over mu. So you can see that rho g, rho here, this is for water, for liquid. So you can see that this part is for liquid and this part is for solid. And K is a combination of them. So this is few confusing points that people may get when talking about Darcy's law. Okay, so Darcy's law is like a constitutive relationship. We're gonna use this word again when we are talking about solid mechanical field. So it's like a constitutive relationship. So let's write down this word here. We're gonna see this word again. Constitutive relationship. And with this constitutive relationship, because we know that if we want to predict or analyze a field, we want to get the governing equation. So to get the governing equation, we can start from the constitutive relationship and the law of conservation. So let's talk about a saturated soil or flow. So for water, let's think about 1 ReV. We know that if we don't use ReV, we can only view the soils as a assembly of particles and water, right? In that case, we cannot apply the knowledge that we learned in continuum mechanics, such as the law of conservation. So in order to do that, we need to assume that the soil has two phases. If we saturate the soil, have water and solid, and they are well mixed within 1 ReV. And another way to visualize it is that we can visualize one point has something like this. Or let's do it in another way. Let's assume that for this ReV, we have, this is 1 point, and we have water in it. This is solid. And this is water. So this is a simple conceptual model. And then, because we have pores, so we have some pathway that the water can move out or move into this point. So this is the conceptual model. And then, in order to derive the governing equation, we need two things again. One is the law of conservation. The other one is this constitutive relationship. That's Darcy's law. So for the law of conservation, just think about what we did before. We learned the general conservation law. We learned how to formulate it using equations, right? The general law for conservation is that the change of a conserved quantity over a unit time, so that's partial something partial t equals, let me write down the general equation. So the general equation says zoom out a little bit. So it's partial something, partial t, so the change of something over a limited time equals the divergence of the flux. In this case, we use H. We showed how to derive it. This is the final differential form. We started from the very beginning, right? We talked about it, how to move through the boundary, and then use the Gauss's law. We can convert a boundary integral to a volume integral, eventually we get this divergence thing. We showed how to do that. Do you guys still remember? See, this is what we did here. When we talk about a conservation law, we said that at the very beginning, that's the change of something, in this REV over unit time equals, this is the summation of, of the flux through its boundary. We need to get a dot product so that we only count, the flux that is vertical to the surface, right? And then next we get we convert, this is the discrete form, so we use summation. Then the corresponding continuous form we use integral. So this VU is the volume integral over dV, and this is through boundary, so it's the surface integral. Then have this. Then we split the left term into two, and for the right term we use the Gauss's law. We said that the surface integral of the flux equals to the volume integral of the divergence of the flux. That's the Gauss's law. And then we keep going. Eventually, we get something like this. So this is the advection. But in this case, in water movement, we don't have this term. So we only have the first term and then this term. And then we can also consider the source term. So basically, these two terms, the flux term and the accumulation term, they're the most significant one. We're going to use this equation a lot. And in this case, theta is the conserved quantity within a unit volume. So what is the conserved quantity in our case? Is the water volume, right? So is the water volume over the total volume. So this is actually called volumetric water content. Can you guys understand it? Is the fraction of the volume taken by water only. And in the saturated soil, we have two phases. So that means V is the summation of VW and V solid. So V is the water volume and the solid volume. And if you have ever taken any courses in soil mechanics or in even in civil engineering materials, you possibly have heard another water content before. It's usually we use W to represent it. And the W is also called water content. It's defined as the mass of water over the mass, not the total mass, the mass of solid. So this one is called gravimetric. So it's based on gravity or based on mass, not volume. So they're different. Water content. And in this course, we're going to use the first one mostly, not the second one. Because the first one is good for deductions, not the second one. So based on the definition of this one, what's the unit of it? The unit is volume per volume, right? So that's going to be cubic meter per cubic meter. So you can understand it as cubic meter per cubic meter or just one. And then next, in order to derive the equation, we combine this one with Darcy's law. So Darcy's law, again, is obtained based on that very simple 1D experiment. So minus H So combine these two things, we will get this. Oh, sorry, I forgot a K. So can we solve water movement problem using this equation? not, right? There's one equation, but there are two unknowns. K is the material property, so it's known. But H is unknown, theta is also unknown. So in order to solve the problem, we need to eliminate one of them. So to do that, we need to find a relationship between H and theta. So this is called theta. So when you are running a simulation, make sure, like I said again, make sure you know how to write the Greek letter. So it's called a theta. Do it in a professional way. So to do that, we can get a relationship. Actually, there's one relationship. That is, some people find that the change of theta is usually proportional to the change of H. And there's a constant between them. It's called S sub S. Is H. So this S sub S has a physical meaning. It's used a lot in hydrology or geohydrology, and this one it is called the specific storage. So it's also a material property. So the meaning of that is the volume of water released per unit decline in waterhead per unit area. And in order to, sometimes, if we are talking about an aquifer in the ground, we can use experiments to get this quantity. And another way to do it is that, you could, this one can be connected to some other more fundamental properties. So that is C S sub S have this equation, have rho WG times C sub S plus phi times CW. And C here means compressibility. So this is the compressibility of solid particles, or solid skeleton. And this, of course, is the compressibility of water. And phi, this is porosity. So porosity is defined as the volume of void over the total volume. And rho G, rho W is the water density, and G is the gravity constant. So sometimes, we don't know S sub S, but as long as we know C sub S, because these two, they're usually, very, they're in a very small range, the values of them. So we can, based on that, if we know porosity, we can estimate it as sub S in a very simple way. So with this equation, eventually we can obtain the equation, the governing equation for water movement. So that is S sub S partial H partial T equals and you can add a source term here if you need it. Let's use G because we use Q for source. Some people use F or G. And if K is a constant, it's not a function of H or X and Y, we can write it in a simple way. It's just K. So if K is a constant. So this is for saturated flow. You can see that there's nothing, no fancy stuff. It's all, what you get all of them from what we know before. The thing that we need to pay attention to is just, the few confusing points here. Atom 1, 2, and 3. And also how we obtain, this gravity equation step by step. You can see that this is the law of conservation, Darcy's law, and this is one more constituent relationship to relate to. Actually, both of them, they are state variables. Theta and H, both of them, they're state variables. But we only have one gravity equation. So that means we need to eliminate one of them. So we need to find a constitutive relationship between these two state variables. And eventually, we only have one dependent variable and one gravity equation. So we can solve it.
I think I'm falling for you.